All right, question 41 for the math subject GRE practice test. We got some more linear algebra here, and it was this problem that inspired me to make a different video, which I'll put right before this one in the playlist, where I kind of review some linear algebra examples, just kind of pick on the most basic transformations, projections, rotations, scaling, and shearing, and think about them in 2 and 3 dimensions. I didn't necessarily create all these examples with this specific problem in mind, but it was this specific problem that caused me to make that video, so hopefully we can use those examples to answer all these different questions. So what we're asked is which of the following statements is true for every 3x3 matrix with real entries. First one, the matrix has 3 linearly independent eigenvectors. That is absolutely not true. So the way I think about eigenvectors is they're vectors that don't get knocked off their span when you apply the transformation. In other words, they're vectors that the matrix just scales. The factor by which they scale is what's called the eigenvalue. So can we think of a 3x3 matrix that does not have 3 linearly independent vectors that get scaled by the transformation? Well, the first one that comes to mind for me would be a rotation. Maybe rotate around the x-axis. Fairly certain that was one of the examples I talked about here. And see, rotations, 3D here. As I talked about in this video, it only has one eigenvalue, and that eigenvalue has a one-dimensional vector space. So it has one linearly independent eigenvector. It certainly does not have 3. Oh yeah, that makes sense. If I rotate 3-dimensional space around the x-axis, the only non-zero vectors that won't get knocked off their span would be those that lie on the x-axis itself. Assuming, of course, that it's not like a 360-degree rotation or something dumb like that. There's lots of other matrices that don't have 3 linearly independent eigenvectors. In fact, there's another one in my example sheet here. I think shearing in 3 dimensions will not produce 3 linearly independent eigenvectors. The specific shear, for example, produces 2 linearly independent eigenvectors corresponding with this eigenvalue of 1. But we don't need multiple examples. I feel like this one's pretty intuitive. We'll call that good. B and C will kind of go together. So I'm going to put those on hold for a little bit. Maybe I'll jump down to D here. D says if M is invertible, then M has 3 distinct eigenvalues. Well, that's also false. In fact, the exact same example that we used up here will work. If we rotate around the x-axis, we have exactly one eigenvalue, lambda equals 1. Here it is. Because those vectors on the x-axis aren't affected at all by the transformation, so they get scaled by a factor of 1. Rotations around an axis are clearly invertible. All you'd have to do is rotate back in the other direction. So D is definitely a false statement. Any other examples you can think of? Because there's one that's even more obvious than this. I mean, I guess there's tons of them, but maybe the most obvious one would just be the identity matrix, right? It's certainly invertible. It's its own inverse. Its eigenvalues are all 1 because it doesn't do a damn thing, so it scales everything by a factor of 1. It's rare that the identity matrix can be used as a counterexample, but I think that would work in this case. You could also scale everything by a factor of 2. I suppose that would work as well. Lots of examples of matrices that are invertible that do not have 3 distinct eigenvalues. I thought E was a little bit ambiguous. Maybe I'm being too picky. It says M has 2 orthogonal eigenvectors. Does that mean exactly, or does that mean at least? I mean, I think either way it's false. So I guess it's not that big of a deal, but I wish they were a little bit more specific here. So let's see, a counterexample here would be a matrix that has exactly 1 eigenvalue, but that eigenvalue corresponds with 2 orthogonal eigenvectors, either exactly or at least. I think we've seen an example of that as well. I think this shearing example in 3 dimensions will work. 1 eigenvalue, 2 orthogonal eigenvectors. Any others you could think of? Maybe an easier example? Maybe one that you're surprised would be a counterexample? All right, what about our identity matrix again? It definitely only has 1 eigenvalue, lambda equals 1, and that eigenvalue corresponds with 3 orthogonal eigenvectors. So if we interpret this to mean at least 2 orthogonal eigenvectors, then the identity matrix would serve as a nice counterexample, as would, I guess, scaling by a factor of 2 or something. But if you want it exactly, then use this shearing example. Okay, so we've narrowed this thing down to 2 options, B and C. The key to figuring out which of these statements is true and which is false is to think about how you find the eigenvalues. So if our matrix is M, eigenvectors are vectors V, such that when we apply the matrix to the vector, all that ends up happening is that vector gets scaled by a factor of lambda. If you think about subtracting this vector from both sides of the equation, you get mv minus lambda v equals 0. We can then factor out a v to get m minus lambda times v equals 0. As I talked about in the video, this is kind of bad notation, I guess, because this is a matrix and this is a scalar. So when I say lambda here, really I mean lambda times the identity matrix. That's for all the nitpicky people out there. I doubt anyone was actually confused with the notation. At any rate, we got this matrix times this vector, and we get this 0 vector as a result. There's 2 ways that can happen. Either the vector itself is the 0 vector, but when we talk about eigenvectors, we assume it's non-zero. So the other way that can happen is if the determinant of this matrix, m minus lambda, is equal to 0. Well, it turns out that the determinant of a 3 by 3 matrix minus lambda times the identity matrix is a third degree polynomial with lambda as the variable. It's called the characteristic polynomial. I'm pretty sure I had to prove that at some point. Maybe it's even obvious, I don't know. We got this 3 by 3 matrix. I don't want to use subscripts, so I'll just throw letters around. This is M. If I subtract lambda times the identity matrix, I'd subtract lambda on the diagonals. And then if I was trying to figure out the determinant of this matrix, well, using my algorithm for figuring out determinants, I'd take A minus lambda, and I'd multiply that by the determinant of this matrix. And then from that, I'd subtract this constant B times the determinant of this matrix, and then I'd add the constant C times the determinant of this matrix. But if you think about how you calculate the determinant of a 2 by 2 matrix, it's this product minus this product. So this is clearly going to be a first degree polynomial. It's going to be linear, and when I multiply it by negative b, it's still linear. Similarly, this will be a first degree polynomial, but this one over here will be third degree because this product is quadratic, and I'm subtracting a constant from a quadratic, it's still quadratic. And when I multiply that by a linear factor, I get something that's cubic. A cubic polynomial minus a linear polynomial plus another linear polynomial is going to be a cubic polynomial. What I'm saying is the determinant of m minus lambda. Let's see, I've used letters up to I so far, so sure, j, why not? Lambda cubed plus k lambda squared plus l lambda plus m for some constants j, k, l, and m. Eigenvalues are just the roots of this polynomial. In other words, values of lambda that make this thing equal to 0. But the fact that this is third degree kind of means that it looks like this, loosely speaking, or this, loosely speaking. Right? It's got opposite end behavior in the negative x and positive x directions. What that means is it must cross the x-axis in at least one point. It's possible that this is a poor drawing and it's crossing the x-axis here and here also. But the fact that we have this opposing end behavior means you have to have at least one x-intercept. Maybe you have 2, and this x-intercept has multiplicity 2. Maybe you have 3, each intercept having multiplicity 1. The point is, cubic polynomials must have at least one x-intercept. And since x-intercepts are roots of this characteristic polynomial, and roots of this characteristic polynomial are eigenvalues, m must have at least one real eigenvalue. By process of elimination, we know that statement B must be false, but it's easy enough to prove why. Statement B says m has at most one complex eigenvalue. That's false because complex eigenvalues would be complex roots of this characteristic polynomial, and complex roots of polynomials always come in conjugate pairs. Right? If 2 plus 3i were a root of this polynomial, then 2 minus 3i would have to be a root of this polynomial. That's what, fundamental theorem of algebra maybe? Or at least a consequence thereof? Anyways, the fact that complex roots come in conjugate pairs tells us that not only is this statement not always true, it's always false. M can't possibly have one complex eigenvalue. It either has 0 complex eigenvalues or it has 2 complex eigenvalues. The correct answer is C, because cubic polynomials always have at least one real root.